All right. Oop. That's not good. So, excuse me. So how many of you guys know what does the fundamental theorem of calculus part 1 say? Anybody? What's the definition of the derivative? Anybody know that? Let's start with that. So the definition of the derivative, you might recall, was that f prime of x was equal to what? It was the limit as h goes to 0 of f of x plus h minus f of x divided by h. You remember this? The start of calculus 1, and then you, well actually before this, what did you do? You learned a bunch of limit laws, right? And you did these calculations with limits. Remember that? And then, so, a lot later, we learned fundamental theorem of calculus part 1, which is what? It says what? It says d dx of the integral from a to x of f of t dt is equal to what? This is so-called FTC1. Do you guys know it? Yeah.
F of x.
F of x. Very good. Now, why is that true?
You're asking me?
Yeah.
Well, because when you, I don't know, honestly.
You don't know, honestly? Yeah, I think that's accurate. I mean, not just for you, but for me too. When I took Calculus 1, this is just something I learned. I never found any of the explanations that I was given in Calculus 1 convincing. And in fact, that's what I'd like to talk about for a minute, because I don't, maybe you know it, but you don't really know why it's true. And there is actually a pretty simple reason. So, if we define the area function, right, we can use the definite integral, right? Integral from a to x of f of t dt. This is just a notation to express the area under the function, right? From 0 up to x, this area function. So if I graph, you know, if my graph for f of x looks something like this. Oh man. What is that? Anyway, there's always a bunch of random stuff in this room. Like this has not been accurate for some time. So suppose this is your y equals f of x, right? So a of x, like let's fix an x, right? If we go to here, right? Then, excuse me, the area, say from 0, right? Well, from a, let's say. So we could start it at 0 if you like, just to make it specific here, right? But for my picture, let me just make it from, oh, fine, from a. Where do you want to put a? I'll wherever you want, right? Could be here. Sorry, I have trouble making decisions. So this is a of x. Excuse me. And then if you go a little bit more, right? If you go a little bit more, you get to where? Let's say x plus, and I'll use a little, here, I'll say x plus a little change in x, right? That would be this piece right here. What's the area of the little piece I just shaded in black?
The integral from x to x plus delta x.
Ah, yes, it would be the integral from x to x plus delta x, that's true. Let's call it, that's a little bit of area, right? That's the change in the area. Like you said, it would be the integral from x to x plus delta x, that's true. But can you tell me something easier? What is that, what's a good approximation to that area? See, this point right here is what? X comma f of x, right? And what's this width right here?
Delta x.
Delta x, right? So the height there is f of x. The width is delta x. So a good approximation to the little bit of extra area is just f of x delta x, right? What happens when you divide by delta x? So we get delta a is equal to, excuse me, have then is that delta A over delta x is what? It's f of x, right? You can see that from this picture. What happens if you take the limit as delta x goes to 0? See, this limit definition of the limit up here, we could have written instead of this h, a lot of times in engineering or physics, you might put a delta x there instead. Don't be confused, it's the same thing. That's just another label. And so in the limit as delta x goes to 0, we get exactly this right here. Because the limit as delta x goes to 0, this becomes dA dx, right? So we have dA dx equals f of x, which is exactly the statement up here. This is FTC1. So it's actually kind of unsurprising if you look at it from this perspective, but at the same time, I never really understood when I first took calculus why FTC1 is even interesting, right? Well, I mean, who cares about this? Do you? Don't answer that. So what was more interesting, right, is FTC2. FTC2 says if big F prime of x is equal to little f of x, right? Then the integral from a to b of f of x dx is equal to big F of b minus big F of a. Right? This is FTC2. What's the big F is with relation to the little f? Big F is called what? A antiderivative, right? And we're assuming here that the little f is continuous. What's the relation between these two theorems? Do you guys know? So, let's see here. So, by FTC1, right, we know what? We know that ddx of the integral from a to x of f of t dt is equal to f of x, right? But what else do we know here? We know that this is equal to ddx of f of x, big F of x, right? So I can call this thing, just to give it a different label, a of x, the area function, right? So I have the area function defined by the integral, and the antiderivative, which I'm just assuming exists at the start of the theorem, and they both differentiate to the same function. What does that mean? If the derivatives of two functions are equal, what does that tell you? They're equal. They're not equal, no. For example, let me show you that. If I had x squared, right, and if I had x squared plus 7, you do the derivative, right? Both of these work out to what? 2x plus 2x, right? So when derivatives are equal, that doesn't give us equality of the the equality of the things being differentiated. It gives us that they're related up to a shift, right? So what we learned is that a of x is equal to f of x plus some constant, right? So notice that the integral from a to here's where I'll get stuck. I don't have time to get stuck today. Wait. So let me just like there's a way to you have to know your weaknesses, right? In this particular thing, there is a I have this bad habit, if I do it the wrong way, it'll eat 10 minutes, Let's not do that. So Here we go. So this is from page 11. That's the handout today. But if we look at, see how it's starting wrong. So we should just look at f of b minus f of a. If you look at that, this is what? A of b minus c, as I've set it up, right? Oh man, I put the c on the other side in the notes. Can I fix it? I'll do it like this, it's fine. This won't quite match what I have in the handout, that's okay. So minus a of a minus c, right? What happens there? So the c's cancel, right? And you're left with a of b minus a of a. But what is that though? If we go back to the other notation, it becomes obvious what that is. A of b is the integral from a to b f of x dx, right? And what's a of a? Well, that's minus the integral from a to a. It's the integral from a to a. This whole construction of the integral breaks down there, right? So that's 0, right? And what is this?
They're equal.
They're equal. What is this, though? This is the fundamental theorem of calculus part 2, right? This is the one that we actually use more often than not, yeah? So let's apply it, yeah? What if you guys wanted to integrate, say, 2x cosine of x squared dx from 0 to 1? How would we do that integral? A u substitution, that's good. Yes, so that is where we're assuming you guys got to last semester. If that's not the case, I'm sorry. Come to my office hours, try to give you some pointers on that stuff. But so we should do what? We should let u equal to x squared. That makes du 2x dx. U of 0 is 0 squared, which is 0. U of 1 is 1 squared, which is 1. So not a great example for changing the bounds. 0 to 1. So the 2x dx becomes du. We just got cosine of u du. Right? And so what's the antiderivative of cosine?
Sine.
Sine, right? So we have sine of u. Use the evaluation bar notation, right? 0 to 1. So that's sine of 1 minus sine of 0, which is sine of 1. Example 2. We got the integral from minus 3 to minus 1 of dx over x. How do we do that one? What's the antiderivative of 1 over x?
Natural log.
I heard natural log.
Absolute value.
I heard absolute value. Which is it? Is it natural log or is it absolute value? Okay, I'm just messing with you. I know what you guys meant. Natural log of the absolute value of x, right? But we evaluate that from what? From minus 3 to minus 1. So that gives us natural log of the absolute value minus 1 minus the natural log of the absolute value minus 3. What does the absolute value do? Just kills minuses, right? So what's the natural log of 1? Well, natural log of 1 is 0. And so the answer here is minus the natural log of 3. Notice that a definite integral, right? An integral with bounds is a number. What other kind of integrals do we talk about?
Indefinite.
Indefinite integrals. But indefinite integral is just another name for what? The set of all antiderivatives, right? So for the most part, we're focused on indefinite integrals. See here, so example 3. Do one of those. What would be the integral of cosh x plus secant squared x dx. Show of hands, who has not seen cosh before? Okay, just a couple. So yeah, we tried to cover hyperbolic cosine. So cosh, if you didn't know, is 1/2 e to the x plus e to the minus x. When I've got more time, I'll talk more about it, just not today. So the sinh x, in contrast, is 1/2 e to the x minus e to the minus x, right? And so if you differentiate sinh, you get the cosh. And if you differentiate cosh, you get the sinh. They're derivatives of one another, there's no minus section. So the integral of cosh is sinh of x. The integral of secant squared is tangent, because the derivative of tangent is secant squared, right? So this example, like unlike my first two examples, we have the plus c, right? Because that's a notation for reminding the reader it's the set of all antiderivatives. So just a moment here. Now, so I wanted to, today, I hoped to cover more, but we're going to have to go on because this is not a Calculus 1 course. So what I'd like you to do is just to read over this PDF, if you would. It's 22 page. It's a 22-page, very just concise. Overview of Calculus 1, but there is a focus here on the things which matter most. Like so, I'll try not to go over time much in here, but today is a slight exception. I'm just going to take a minute. I mean, if I start 4 minutes late, I should end 4 minutes late, right? I'm just kidding. So I'm going to start with a review of Calculus 1. We have the product rule. We have the quotient rule, we have the chain rule, you need to know those. Here's a list of all the derivatives that we know from Calculus 1 right here, in all their glory. Here's a reminder on how you can differentiate inverse functions, how you derive the derivative of inverse functions using implicit differentiation. Here's a reminder about the role between increasing and decreasing in positive and negative derivatives, right? There's the closed interval method. You'll need that for some of the homework problems. There's a reminder of what the definition of the integral is here. That's going to be important to us in a few weeks. I don't really cover numerical integration in here. But anyway, if you would, just please, read through this, make sure that you've seen these things, and we'll just kind of go forward from there. At the end of this, there is just a laundry list of the integrals you got to know, right? So like the quiz tomorrow, it's not going to be on the theory part. It's just going to be on this is differentiation, this is integration, just a quick kind of check on where you are on the basic differentiation integration from Calc 1. So that's all I got to say today. Thanks, guys. Again, sorry I was late. I'll try to do better tomorrow.
We'll have to follow up on